Hello students, welcome to AIMS online classes. This is a chemistry session. Here we are going to discuss about structure of atom. In this session, we are going to say about electromagnetic waves. We have learned in the previous classes about subatomic particles like negatively charged particles like electrons, positively charged particles like protons, and even about electrically neutral neutrons also, isn't it? We have studied about these particles which are called as subatomic particles, isn't it? Yes, not only that, and also we have acquired some fundamental ideas about atomic models which were suggested by different scientists, isn't it? For example, J. Thomson's watermelon model and Ernest Rutherford's planetary model of atom. We have studied it. And even Niels Bohr, which have been presented in class 9. So about this all, in the earlier classes we have studied about the subatomic particles as well as the atomic models which were suggested by different scientists. Now, let us understand the nature of light, colored flames and their characteristics. Okay? Spectrum. You must have observed the formation of rainbow. Did you observe ever? Yes, when it rains at a certain time, we may observe often rainbow in the sky. There are 7 colors, namely violet. See here the rainbow colors: violet, indigo, blue, green, yellow, orange, and red. So these colors will be seen in the rainbow, isn't it? Yes. Simply we call these all colors together as Vibgyor. You can find the colors spreading continuously and the intensity of each color varies from one point to another point. See here, the intensity of a color will be varying from one point to another point. Suppose if you see this yellow color itself, here the intensity of yellow color is somewhat less, but here the intensity is somewhat greater, and it is somewhat less here again. Means the intensity of each color varies from point to point, and these all colors spreading continuously one after another. Okay. Wave nature of light. When you throw a stone into a still pond, what do we observe? Have you ever done this? If we throw a stone into a still pond, you observe ripples which are transmitting the disturbance in the form of waves, isn't it? Yes, when you throw a stone into a pond, still pond, we observe some ripples which are transmitting the disturbance in the form of waves on the surface of water, isn't it? You know that sound waves are produced when something vibrates. For example, like drums. When you hit the drums, some sound waves are produced. So when the drum is vibrating, it produces sound waves. In the same way, electromagnetic waves are produced when an electric charge vibrates. So how these sound waves are produced when something is vibrating, like drum? How these waves are produced on the surface of water when we hit with a stone? In the same way, electromagnetic waves are produced when electric charge is vibrating. When an electric charge vibrates, electromagnetic waves are produced. Okay. So what are these electromagnetic waves? Let us see here. A vibrating electric charge creates a charge in the electric field. Sorry, a vibrating electric chain. What is that? A vibrating electric charge creates a change in the electric field. Yes, when the electric charge, if it is vibrating, it creates some changes in the electric field. The change, the change in the electric field creates a change in the magnetic field also. So in this way, when electric charge is vibrating, it creates some changes in the electric field. The changes in the electric field changes create some changes in the magnetic field. In this way, when an electric charge is vibrating, there will be changes in the both electric field as well as magnetic field. This process continues. So until and unless this electric charge is vibrating, the changes in the electric field and magnetic field will be continued, with both the created fields being perpendicular to each other and at a right angles to the direction of the propagation of the wave. See the diagram here, picture given. If this is the wave propagation direction, and this is magnetic field. This green blue light representing magnetic field, and it is electric field. So in this way, these two are getting changes, magnetic field and electric field. These changes are being continued. And if you observe, this electric field and magnetic field are being both perpendicular to each other. At the same time, these two are being perpendicular to the direction of the propagation of the wave. Okay, in this way, when a electric charge is being vibrated, it creates some changes in the both electric field and magnetic field. It will be continued, and these electric fields and magnetic fields are being perpendicular to the direction of the propagation, and they be perpendicular to each other also. Visible light is an electromagnetic wave, and the speed of this visible light is 3 into 10 to the power of 8 meters per second, or 3 into 10 to the power of 10 centimeters per second. So in this way, visible light is also an electromagnetic wave which travels with a speed of 3 into 10 to the power of 8 meters per second. Now let us see here the characteristics of these electromagnetic waves, just like the visible light. Electromagnetic energy traveling through a vacuum behaves in some way like ocean waves traveling through water. Yes, these electromagnetic waves behave like the ocean waves which are traveling through water. And these electromagnetic waves can travel through even vacuum also. They travel through medium as well as vacuum. Actually, they do not need any medium for their propagation. So, like ocean waves, electromagnetic energy is characterized by wavelength and frequency. So, how these ocean waves are having certain wavelength and frequency? In the same way, these electromagnetic energy or electromagnetic waves also characterized by wavelength and frequency. What is wavelength here? The wavelength of a wave is the distance from one wave peak to another wave peak. To say simply, the distance between the two nearest troughs or crests of a wave is called its wavelength, and it is denoted with the symbol lambda. Okay, and what about frequency? The frequency of a wave is simply the number of wave peaks that pass by a given point per unit time. It is expressed in units of reciprocal seconds or second inverse. What is frequency? To say simply, the number of waves passing through a point per second is called frequency of that wave. Whether it is a electromagnetic wave or any light wave, whatever it is, or whatever it is, sound wave, whatever it is. So if the number of waves passing through a point per second is called its frequency, it is denoted with the symbol nu. So what will be its units? We are telling it is the number of waves passing through a point per second. Number of waves per second. So that per second or second inverse or reciprocal second is its unit. The relation between these two quantities. That means the relation between wavelength and frequency. Actually, this frequency and wavelength are inversely proportional to one another. That is, mathematically, we can express like this. Nu is directly proportional to 1 by lambda. That is equal to remove the proportionality, we have taken a constant here. By that it became nu is equal to C by lambda, where nu representing frequency of the wave, lambda is wavelength of that electromagnetic radiation or electromagnetic wave, and c is a constant called velocity of light. What is the velocity of light? It is equal to 3 into 10 to the power of 8 meters per second, or 3 into 10 to the power of 10 centimeters per second. Okay, we can apply this equation to a sound wave also. Yes, not only for electromagnetic waves, we can apply this equation which is relating frequency and wavelength of a certain wave. This also can be applied to even sound waves. It is actually to say it is a universal relationship and applies to all waves, not only for sound waves, not only for electromagnetic waves. This can be applied for all types of waves which are having wavelength and frequency. As the frequency increases, wavelength becomes smaller. So as frequency and wavelength are reciprocal or inversely proportional one to another. If frequency increases, wavelength decreases, vice versa. So this relation can be applied for all kinds of waves. Electromagnetic waves can have a wide variety of frequencies. The entire range of electromagnetic wave frequencies is known as the electromagnetic spectrum. So these electromagnetic waves are having different frequencies. They'll be having different frequencies. Different waves will be having different frequencies. If all these waves are written together, then that is called electromagnetic spectrum. So if all ranges of electromagnetic frequencies are given together, all together, then that is called electromagnetic spectrum. The familiar example of the visible spectrum in nature is the formation of rainbow. See, in the rainbow what we see, there will be 7 colors, each color representing one kind of electromagnetic frequency. So if these all frequencies are being together, nearly 7 kinds of frequencies are shown there, because 7 colors are being appeared. So all together they are. Those altogether frequencies known as electromagnetic spectrum. So for the electromagnetic spectrums, fine example is a rainbow. Each color in a rainbow is characterized by specified wavelength and specified frequency, isn't it? So this wavelength is from red to violet. Each color representing specified with some wavelength and particular frequency. This ranges from red color to violet color. So red color will be having higher wavelength, that means lower frequency, and it increases slowly the wave, what is that, frequency slowly increases from red to violet, that means wavelength decreases from red to violet. So violet is having the shortest wavelength among these 7 colors, and which represents the higher frequency. So red is having lower frequency, violet is having higher frequency. So frequency ranging from red to violet gradually increases. So in terms of wavelength, what happens? Red has a greater wavelength, whereas violet is having shorter wavelength. These colors that the human naked eye is sensitive to observe are called visible light. Actually, the colors which are seen, which can be seen by naked eye, the spectrum, the range of the series of frequencies which are seen by naked eye of human, are called visible light and visible spectrum. The range of wavelengths covering red color to violet color is called the visible spectrum. Okay, these we can see. So those color spectrum which we are able to see is called visible spectrum. So electromagnetic spectrum. Electromagnetic waves can have a wide variety of wavelengths. Yes, we told already this. Different waves are characterized with different wavelengths. The entire range of wavelengths is known as electromagnetic spectrum. Okay, if these all different kinds, all the ranges of wavelengths are written together, then that is called electromagnetic spectrum. The electromagnetic spectrum consists of a continuous range of wavelengths of gamma rays at the shorter wavelength to radio waves at the longer wavelength. but our eyes are sensitive to only visible light. See here, they have shown electromagnetic spectrum in which different waves, electromagnetic waves, the different wavelengths are written in a series, either in the decreasing order of frequency or increasing order of wavelength they are written. First you see they have given gamma rays which are having shortest wavelength or greater frequency, and at the last radio waves and TV waves, these all are there. So these are having the lowest frequency or greatest wavelength. This arrangement of different kinds of electromagnetic waves in the order of their either increasing or decreasing of frequency or wavelength is called electromagnetic spectrum. So there are different color, the kinds of electromagnetic waves. But out of these all, only a certain range of electromagnetic radiation only can be seen with our human eye, naked eye. That range is called visible radiation. See here it is. It is expanded to observe clearly. This range only is visible to human eye. This range spectrum is called visible spectrum. In this only we can observe this Webjar. 7 colors are in this visible light radiation range. This spectrum which is visible is called visible spectrum, but this is a complete electromagnetic spectrum. When you heat an iron rod, some of the heat is energy, some of the heat energy is emitted as light. First, it turns red. So what happens when you heat an iron rod? First, it turns into red color. See here, it is in red color. And as the temperature rises, it glows orange. Slowly the color changes to orange and then yellow color. Finally, if you heat it very at high temperatures, it goes to blue color, and after reaching the higher energy it converts to even white color also. If the temperature is high enough, then it glows with the white color as it is heated at very high temperatures, isn't it? Yes. When the temperature is high enough, other colors will also be emitted. But due to higher intensity of one particular emitted color, the other colors will cannot be observed. So, as it is being continuously heated in iron rod, at the starting it may be seen in the red color, and slowly the color changes as heat increased. Orange, yellow, and blue color also. And at very high temperatures, it seems in the white color glowing. So when the temperature is being high enough, almost all the colors will be seen. Almost all the colors are emitted. But out of this, one is having the higher intensity than others. So that is only being seen, remaining cannot be observed. Max Planck broke with the continuous energy tradition of electromagnetic energy by assuming that energy is always emitted in multiples of h nu. Yes, till before him, all scientists they have assumed that energy is being continuous. So the energy emitted by the particles is being continuous. But Max Planck broke this tradition. He has concluded and given conclusion that energy is not emitted in the in continuous form. Energy is emitted in the small packets form. Each packet of energy is called quanta, and the energy of each packet of energy is equal to h nu. Okay, in this way, he given statement that energy is not emitted by the particles or absorbed by the particles in continuous form. It is instead of being continuous, it is being discontinuous. It is being in the form of small packets. These small packets of energy are called quanta or photons. The energy of each photon or quanta is equal to h nu. So he assumed that the energy is always emitted in multiples of h nu. For example, h nu, 1 h nu, 2 h nu, 3 h nu, and so on till n h nu. In this way, the energy is emitted in the multiples of h nu. Okay. That is, the energy for a certain frequency E can be represented by the equation E is equal to h nu, where h is Planck's constant, which has a value of 6.626 into 10 to the power of minus 34 joule second, or 6.626 into 10 to the power of minus 27 erg second. And here nu is the frequency of radiation absorbed or emitted. Okay, the energy of a certain radiation is given by the equation E is equal to h nu, where h is Planck's constant and nu is the frequency of that radiation. The energy E for the red color is lower compared to the energy of blue color, because the wavelength of red color is higher, whereas frequency is lower. But for blue color, wavelength is lower and frequency is higher. So energy is higher for blue color, whereas for red color it is lower. The energy emitted from a material body increases with increase in heat energy. Yes, when heat energy is increased, the energy emitted from a material body also increases. The significance of Planck's proposal is that electromagnetic energy can be gained or lost in discrete values and not in a continuous manner. Yes, Max Planck proposed that energy or electromagnetic energy can be either gained or lost by substances in discrete form, in discrete values, but it is not continuous. It is in discontinuous form, in the small form of packets. Hence, emission or absorption of light spectrum is a collection of group of wavelengths. That is why it won't be continuous. Even the emission spectrum or absorption spectrum of light is being a collection of group of wavelengths. It is not being all together. So if you take a pinch of cupric chloride in a watch glass and make a paste with concentrated hydrochloric acid, take this paste on a platinum loop and introduce to non-luminous flame. What do we observe? So what they're asking to do here? They're asking to heat cupric chloride on the Bunsen burner or non-luminous flame. Then this cupric chloride produces a green colored flame. See here they have shown the picture how cupric chloride burns. Cupric chloride burns with green color flame. Instead of this, if you take same quantity of some other substance like strontium chloride, it produces some different color. So here strontium chloride produces crimson red flame. If we take some other calcium substance, calcium chloride, it burns with a brick red color. If we take barium compound, it burns with the apple green flame. In this way, each compound burns with, each substance will burn with a different colored flame. So scientists found that each element emits its own characteristic color. It won't be the same with the other colors. These colors correspond to certain discrete wavelengths of light and are called line spectra. So each element will produce a characteristic color. These colors correspond to certain discrete wavelengths. So as there are wavelengths are different, their colors are being different. These all lines together called as line spectra. The lines in atomic spectra can be used to identify unknown atoms. Yes, just like fingerprints are used to identify people. Yes, here each element is characterized with a particular color and even with particular atomic spectra. It will be different from remaining elements. An atom or an element is characterized with certain flame color as well as certain atomic spectra. So these atomic spectra can be used so for identifying unknown atoms, just like the fingerprints how we use to identify people. Okay, thank you for watching our video. Please subscribe our YouTube channel AIMS Today for latest updates and recorded videos.